A very long line of charge that lies on the z-axis produces an electric field that has cylindrical symmetry, given by the electric field equals E naught times the quantity r squared over r naught squared times r unit vector, where E naught and r naught are constants, and where unit vector r hat lies in the xy plane. Calculate the electric flux through a closed cylinder of length L and radius r that is centered along the z-axis. Well, this says we have a very long line of charge that lies on the z-axis. Let's illustrate that on an xyz coordinate system. The z-axis will be vertical, the y-axis will be horizontal, and the x-axis will be coming out at us. Our line of charge is parallel to the z-axis and lies along the z-axis. And this is a very long line of charge, so for all intents and purposes, we could consider the length of this charge to be infinitely long. At least that's what the code words very long line of charge means. Well, being on the z-axis and being a very long line of charge, we know that the electric field will be cylindrically symmetric. And they give us that clue by one, saying the electric field has cylindrical symmetry, and two, saying that the unit vector r hat lies in the xy plane. So in other words, r hat could have any orientation as long as it's in the xy plane. So for example, I'll just draw r hat along the x-axis. If r hat is along the x-axis, then that would indicate an electric field line that is along the x-axis. If r hat is along the y-axis, then that would indicate an electric field line along the y-axis. R hat could be in any direction in the xy plane. R hat is just our unit vector indicating the direction of the electric field. So notice that is cylindrically symmetric. Well, let's take a top-down view because you might not be able to see that so well from this vantage point. If we take a top-down view looking down from the positive z-axis, the x-axis would be pointing straight down, the y-axis would still be pointing to the right, and we have the line of charge is lying parallel and on the z-axis, and the electric field is cylindrically symmetric. So what that means for us is the electric field vectors, the electric field lines, point radially away from a line of charge and has spherical symmetry. For us, what that means is if we were to take a surface, any surface, we'll call our surface a Gaussian surface. This is just an imaginary surface. It doesn't have to be a real surface in space. But what cylindrically symmetric means is everywhere on this Gaussian cylinder, the electric field looks the same. Well, going to our top diagram, let's draw the cylinder in our top diagram. So in our top diagram, the cylinder looks something like this. This cylinder is of length L, and it is of radius R. Notice the electric field lines cross the cylinder. And because it crosses the cylinder, we know that there is electric flux. Now, the top diagram isn't really fully representative of the electric field because since it has cylindrical symmetry, we could draw electric field vectors coming down this way. And up here. And anywhere through. For us, looking at the top-down view gives us a really nice perspective of the relationship of the electric field with the area vector. Our goal is to evaluate the electric field due to this line of charge. Or let me rephrase that. Evaluate the electric flux due to this line of charge where the electric field is given by E equals E naught times the quantity R squared over R naught squared times the R hat unit vector. From this, electric flux would be given as the integral over the surface of the dot product between the electric field and the area vector. But here's the thing. This is a closed cylinder. If we look at the cylinder from the side again, the cylinder has a top, the cylinder has a bottom, and the cylinder has a side. Let's label those. If we look at the top has a certain area. I'll call that area of the top. If we look at the bottom has a certain area that is the same area as the area of the top. I'll just abbreviate these as A sub t and A sub b for the area of the top and the area of the bottom. Therefore, the area vector for the top, well, if we go back to our coordinate system where we have x coming out, y, z going up, the top area vector has a normal vector that is parallel to the z-axis, the positive z-axis, while the bottom area vector has a normal vector that is parallel to the negative z-axis. Now, by convention, if we have a closed surface, area vectors always point outside and away from the surface. So this is why I drew the area vector for the top cap of the cylinder to be going straight up, because that's leading out of the cylinder, and the area vector at the bottom cap going straight down, because that is leading away from the cylinder. Now there's one more side, and that's the side. So the side is coming out, and let's represent the area vector for the side. So I will call this A side, and I'll abbreviate that as A sub S. Now the area vector for the side isn't unique. Depending on where you are on that cylinder, your area vector is going to change. Right now, the way I drew that, the area vector is coming out at an angle on the cylinder. So I'll indicate the area vector here, area of a side. But we could go to a different portion of the cylinder, and that's a different area vector because it's in a different direction. And so where you are on the cylinder matters. And you know what? I'm not even being really 100% accurate, and I should be. The way I drew this, I drew an area vector at a particular point on the cylinder. Well, what we're going to really need to do is we're going to really need to look at tiny pieces of area from the cylinder. So technically, I should have probably called this a area vector differential, or a differential of the area at that point, and the differential of the area at this point, because really we could be looking at very tiny pieces of area on our cylinder. And the reason why I am looking at the area vector differential, let me erase this a little bit. It's because the area vector is changing depending on where we are on the cylinder. It matters, but maybe not. And you'll see why I say maybe not. The main point I want to get across right now is to evaluate the electric flux over this closed surface. We're going to have to evaluate the flux on each of the surfaces. The total electric flux will be the electric flux due to the top surface, plus the electric flux due to the bottom surface, plus the electric flux due to the side. Now, I already know that the electric flux through the top surface and the bottom surface will be equal to 0. And you're wondering, how do I know that the electric flux through the top surface and the bottom surface will be equal to 0? Well, that's a really good question. If you, again, look at the electric field lines, the electric field lines do not really cross that top surface. They might lie in the top surface, but they're not crossing the plane of that top surface. Well, another way of saying that is the electric field is perpendicular to the area vector of the top surface. And we know previously that if the electric field is perpendicular to the area vector of the surface through which it crosses, then the electric flux is 0 due to the cosine of the angle. The same is true for the bottom surface. I know conceptually that the electric flux through the bottom surface is 0 because no field lines are passing through the surface. Rather, the electric field vectors are all perpendicular to the area vector of the bottom surface. So I know those two electric fluxes will be 0. Now, if you're not convinced of that, I will show why they're 0 mathematically. But for now, conceptually, this is what you want to remember. If the electric field is perpendicular to the area vector of the surface in which it crosses, then it doesn't cross the surface. So I even said that wrong. I should have said if the electric field is perpendicular to the area vector of a surface, then no electric field can pass through the surface, and therefore the electric flux is 0. Now, looking at the electric field through the side, the electric field through the side will produce a flux that is not zero. And we're going to evaluate that. But let's take all of this to the next page. I'm going to rewrite our total integral. And the first thing I'm going to show you is why the electric field through the top, or let me rephrase that, why the electric flux through the top surface and the electric flux through the bottom surface are both equal to zero. So beginning with the top surface, I have the electric flux through the top surface, which I'll abbreviate with a T now, is equal to the surface integral through the top surface of the electric field passing through the top surface dotted with the area vector of the top surface. This is just the surface integral through the top surface times the magnitude of the electric field through the top surface times the magnitude of the area vector through the top surface times the cosine of the angle between the electric field and the area vector through the top surface. Now, the angle, let's look at our previous page. The angle between the electric field and the area vector of the top surface is 90 degrees. So this is 90 degrees, and the cosine of 90 degrees is 0. This means that the electric flux through the top surface is equal to 0. Similar for the bottom surface. The electric flux through the bottom surface is equal to the surface integral through the bottom surface of the electric field passing through the bottom surface dotted with the area vector of the bottom surface and remember, this is just the magnitude of the area vector, or the magnitude of the electric field through the bottom surface times the magnitude of the area vector of the bottom surface times the cosine of the angle between the electric field and the area vector. Once again, we know that the angle between the electric field and the area vector through the bottom surface is equal to 0, which means this integral evaluates to 0. And just for your notes' sake, since I put a line through that angle theta, I'll just label this right here to be 90 degrees, which makes the cosine of 90 degrees equal to 0. And that's why the electric flux through the bottom surface is equal to 0. Now that we've done that, just remember, anytime an electric field is perpendicular to the area vector of a surface, then the electric flux due to that electric field is 0. Well, now let's do the electric flux through the side. I am going to just redraw my cylinder, and I'll go ahead and indicate my coordinate system. The z-axis is going up, And here I'll do a dotted line on the inside. The y-axis is horizontal, and the x-axis is coming towards us. And here I'll do this for the xy plane for some perspective. Well, let's take an area vector. For simplicity, let's just go ahead and position our area vector. Actually, let's position it somewhere else on the cylinder. I'll position it right here for a tiny bit of area coming out of the side. That tiny bit of area is like a representative polar rectangle. So here is our tiny bit of area. We know that the electric field has cylindrical symmetry. So I could just again illustrate that with some lines. Okay. So having cylindrical symmetry, I know that the electric field is going to be parallel to the area vector at the point of our representative polar rectangle. So I'll label that electric field vector right here. Let's look at a top-down view looking down from the positive z-axis for perspective. If we are looking down from the positive z-axis, then the x-axis will be going down, the y-axis will be going to the right. Here is our cylinder. This cylinder is of radius r, and over here I'll indicate that the length of the cylinder is length L. From this perspective, let's go ahead and illustrate our electric field lines having cylindrical symmetry. And these electric field lines are due to a line of charge a very long line of charge that lies on the z-axis. Let's now look at a representative polar rectangle on our cylinder. That representative polar rectangle has a tiny bit of area. Here is that tiny bit of area differential, which I'm going to call it the area differential for the side. And I'll illustrate an actual electric field vector at that polar rectangle, which is indicated right here. Notice that the electric field is parallel to the area vector. That's going to help us out a lot in our calculation. So let's write down the electric flux through the side is equal to the surface integral of the electric field through the side. Well, let's look at the electric field vector. The electric field vector has components of E naught times the quantity r squared over r naught squared, r hat unit vector, the infinitesimal area vector through the side has a tiny bit of area, and since it's cylindrical, that will also be in the r hat direction. So the dot product between the electric field vector and the area vector is equal to, well, we could take the dot product of the components. That's easy because they both have the same component. E naught r squared r naught squared is the r hat component, or the radial component of the electric field. And this is going to be times the radial component of the area vector. So I just took the components, since that was the easiest to do since they had the same components. I could have also calculated this by taking the magnitude of both sides and then doing the cosine of the angle between the two vectors. And we know the angle is 0 degrees. We'd end up with the exact same result that we have here. So with this said, now we have the electric flux through a side is equal to the surface integral through that side of E naught r squared over r naught squared times the area vector. Now, the electric field is to be evaluated at the surface of the cylinder. Here, the surface of the cylinder, the surface of the side, is a distance capital R away from the z-axis. So I can rewrite the electric flux through the side as E naught capital R squared for the radius of the cylinder over r naught squared, which is some constant, times the surface integral of the area that we are interested in, the area of the side. Well, the integral of just a differential, in this case the differential for the area of a side, is just going to be equal to the area of the side. Well, now we have to determine the area of the side of a cylinder. Well, we could do that really easily. Let's look at our cylinder again, just a quick sketch. That looks pretty bad. Let's try that again. Okay, this cylinder has a length L. This cylinder has a radius R. If we imagine slicing that cylinder down on one side and expanding that side out, forgive me, that was supposed to be an arrow, and expanding that side out as if we are unrolling that cylinder. That cylinder's height is L, and the length of that cylinder is 2 pi r for the circumference of a circle, which means the area of that side of the cylinder is 2 pi r L. This means that the electric flux through the side of the cylinder is equal to E naught r squared times 2 pi r L over little r naught squared. And this is just 2 pi E naught L r cubed over r naught squared. And so the total electric flux then, remember, that was the electric flux through the top surface plus the electric flux through the bottom surface plus the electric flux through a side we showed that the electric flux through the top and bottom surfaces are 0, which means that the total electric flux through the cylinder is given by just the electric flux through the side of this cylinder for this line of charge with cylindrical symmetry, and that's equal to 2 pi times E naught L R cubed over R naught squared.